Okay, it's started. So everyone, welcome to Origins meeting. And today's speaker is Dániel Apai. He's a professor at University of Arizona at Department of Astronomy and Planetary Sciences. So he has double position, enjoying all the meetings in both departments. I first met Dániel as postdoc here. I think it was 2003. And then we worked for, at that time there was an astrobiology program led by Michael Meyer. And then we lost him to Space Telescope Science, STSCI, and he was there as an assistant astronomer. Then we successfully recruited him back as a faculty. So we were very lucky to have Dániel here. And he will talk about a very exciting program. He's a PI of a huge program, including Earth Nexus, Earth and Other Systems program, and a couple of others. And we'll hear something very interesting about Nautilus today. So Dániel, the floor is yours.
Thank you, Serena. Thank you all for joining today. I'm very excited to tell you about a project that we started about 4 or 5 years ago, and it has a crazy idea, and it has grown from a very small group of people into a fairly large project now. I'm very excited about the progress we have made, and I hope you will find this interesting. I should mention that I was down selecting the slides from about 200 or so slides, so there's much more material than what I would be able to cover now. I will try to leave some time at the end for questions, but if we cannot get to your questions or you have other questions, let me know via email, and then I'm happy to provide more information. So the talk itself is entitled 1,000 Earths, Ultralight Telescopes for Biosignature Surveys. And what I will explore here is the idea that we could and we should build a space telescope that allows us to probe a very large number of broadly Earth-like planets so that we have a deeper understanding of these worlds. And you see our team, members of our team, others have also contributed in different ways. And I wanted to recognize in particular the Betty and Moore, Gordon and Betty Moore Foundation that is funding most of the work that you see here. So I usually don't do outlines for talks, but this one is complex enough that I thought this will be useful. First, I will speak very briefly about the motivation behind trying to observe 1,000 exo-Earth analogs. And then I will introduce a new technology that will allow us hopefully to reach this goal. I want to show you ongoing design and hardware development, concept development, and describe the Nautilus Space Observatory, which is the full implementation of the observatory, and the Nautilus Probe, which is a probe class mission that is the first major step toward realizing the flagship-class space observatory. Okay, so I just wanted to put out some of the ideas that exist, some of the tools that we will have or we may have soon to study exo-Earths. And you recognize James Webb, which is launching hopefully next year. James Webb will expand, of course, the light collecting area that we currently have, the largest, that is the Hubble Space Telescope, and it will be able to study exoplanets, but it was not designed really to search for life, and it is going to be very challenging with James Webb to really study Earth's analogs. Our best chance is probably to do transmission spectroscopy of transiting planets, aim for a handful of planets, perhaps even fewer, that are around the right targets, very nearby, for which James Webb has enough light collecting area to study their atmospheres. And realistically, it's going to be a handful of planets, and in which something like biosignatures or good indicators, possible indicators of life can be searched. It's a very exciting mission, but it has its limitation in terms of biosignatures, which is of course well known. This in part sparked a next generation of flagship ideas. I show here one of these concepts, the LUAR concept, which its most ambitious version is about a 16-meter diameter mirror-based telescope that is building on the general technology that James Webb is developing, but pushing it also to the shorter wavelengths, even in the ultraviolet. And this telescope will, if built, will use high contrast imaging to suppress starlight and then directly image and carry out spectroscopy on exo-earth analogs and study them. So here, the expectation is that LUVOIR will be able to search for something like search for and characterize maybe 30 to 60 planets broadly similar to Earth. It will study a larger number of planets, but really those that are habitable, possibly habitable and exo-Earth planets, it probably will be a sample of that size. It's an order of magnitude greater than what we can hope to get from James Webb, and it is a very exciting mission. We have to ask the question, however, at some point, what if we need more? What if we need a larger sample? And this question is important to ask and explore, because if you now think that you had a sample of 10 or maybe 50 stars to study, and then you would want to understand stellar astrophysics, or you had, say, 10 or 20 or 30 galaxies, and you would want to understand galaxy evolution, and even understand maybe if there are special classes of galaxies within those, with the complexity of an alien ecosystem, right? What is really the sample size that you need? And small samples are very exciting, and that's necessarily how we explore a new category of objects. But eventually, we want to do statistical studies that require larger samples, especially if you think about the possible complexity of these worlds coupled to alien ecosystems. So a couple of years back, we started a small group. We started to explore what would it take to study 1,000 exo-Earths. How could we do it? The way we looked at this problem was that we felt that we have to try a different path than what, say, LUVOIR is pursuing. And I will show you why we are pursuing that and what opportunity we see emerge. The science goals for the concept that we tentatively call Nautilus is very simple, and they resemble others explored by the community, but there's one important difference. So our science goals are to determine the diversity of Earth-sized planets and then to search for life. The science objective, really what we want to do in terms of the observation, is to spectroscopically characterize about 1,000 Earth-sized habitable zone planets. So the emphasis here, what makes this really different and what everything flows from that number here, is about the 1,000. We want something that is providing statistical samples and something that is scalable. So how can we do that? What we decided to do is to look into using the method that currently has discovered the greatest number of small planets, and the only method currently that allowed us as a community to study these smaller planets and their atmospheres, and that those are transits. So let's start with this simple question, and this is something that we published in an astronomical journal paper that appeared last year, and you will find many of the figures and etc. You can refer to that paper for further information from this talk. So we can explore knowing Kepler recurrence rates, at least approximately, for small planets around different spectral type stars, how far in space, at what distance we need to look if we are to find and characterize 1,000 Earth-sized planets. So if it depends greatly actually on the sample. If you are satisfied with looking at the 1,000 closest planets, you can probably find those mostly around M dwarfs. These are again habitable zone Earth-sized planets. You can probably find those within 55 or so parsecs. If you want more sun-like stars, FGK type stars, you need to go a bit further out. But you would find within 160 parsecs or so, you would find that many transiting Earth-sized habitable zone planets. And if you restrict your sample to only sun-like stars, you would probably need to go out to about 330 parsecs. So the exact values for eta Earth and the more specific definition will impact these numbers a bit, but not greatly. And the specific numbers really don't impact the mission concept I'm going to show you because of its inherent scalability. So the idea here is to do transits, use transit spectroscopy to characterize the atmospheres of these planets. And have a telescope that is capable of studying about 1,000 of those. It turns out that even though the actual distances depend on what spectral types you choose, the brightnesses of the stars at those distances are actually quite similar. So in terms of the telescope size, there's not a great difference between which host you choose. So could we do with transit spectroscopy, could we look for biosignatures, understand how planetary atmospheres are made? This should come at no surprise. We are doing that. That is basically one of the highlights of science, for example, both from Spitzer and the Hubble Space Telescope recently in exoplanets, not Earth-sized planets and not habitable planets, but smaller, increasingly smaller planets. What you see here are simulations that show that if you were able to take transmission spectra of Earth analogs at different distances and on different spectral type stars. So on the top, you see sun-like stars at 100 parsecs and 300 parsecs. So the top right would be the farthest representative to the farthest targets. The top left would be a target that is closer to us. Or if you were to do similar observation around M dwarfs in the lower panel, you can see that you can add up these observations. You don't need too many of them. And you could build up a signal to noise that's sufficient and could be actually very, very good also at a more nearby part of the sample to recognize the key absorbers in these atmospheres. So you can do this. One thing I want to point out that you see here the Y scale, which is the transit depth as it changes with the wavelengths. You can see that we are speaking here about parts per million level signal. And that sounds daunting, and it is daunting. But in terms of the stability, this is something that is already currently the state of the art. Kepler on the brightest stars can reach or was able to reach 2 parts per million. So in terms of the stability, this is not something where we need decades of development. Here, we are not relying, again, just for everyone's sake who is not familiar with it, we are not relying here on high contrast. We are not relying on very high image quality. What we rely on is sensitivity, collecting enough photons to carry out this measurement. So of course, why we cannot do this today is that we cannot collect enough photons. So what I didn't tell you yet, and what I'm going to tell you about the rest of the talk and show you how this may be possible, is that to do these measurements, we would need an enormously large space telescope. And 50 meters sounds crazy, but I will try to show you why this is actually something that we may be able to do in the near future. So I will just, when we call this concept.
We have a question in the chat. So Ravi asks, which telescope are the simulations for that you have done?
So I showed simulations for let me try to go back here with the slides. It's kind of going forward. So the simulations that I showed you here were for a 50-meter diameter telescope. And you can find a complete description of the simulations in the Astronomical Journal paper. So let me add this, that if you have clarification type questions, I'm happy to take them during the talk. If it's a more in-depth question, maybe let's do those towards the end, okay? Okay, so basically just a comparison, baseline, how this would compare. If we had Nautilus Observatory, it would have a collecting area about an order of magnitude greater than, say, the LUVOIR, most ambitious versions of LUVOIR. It would be able to study, in fact, it is designed to study 1,000 habitable planets and search for life, that sample. And it would be able to search for these biosignatures to a much greater distance, about 100 parsecs, but it's also somewhat scalable, as I will show you. Okay, so obviously everybody knows that we cannot now build a 50-meter space telescope, and it sounds even crazy to consider this, but it is very important to actually ask the question, what stops us now from building a 50-meter space telescope? Why we cannot do this? And there are a couple of things, and I will show you this, so let me show you some examples. If you think back in the 1980s, okay, on the top left, you see the most elite communication device that existed then. This was a cell phone that you could actually carry with you if you were really wealthy and make phone calls. Today's cell phone, of course, we are all familiar with the iPhone. Maybe it's interesting to point out that an iPhone X now carries more computational power than the world's 500 fastest supercomputers in the 1980s. Okay, it's an enormous increase, and we are all familiar with it. We are used to this. But let's take a look how did it map this progress that we witness and we live with to space telescopes. So in the 1980s, the most capable space telescope that was designed and then launched in 1990 was the Hubble Space Telescope. And now 2020, no surprise, it is still the Hubble Space Telescope. It's an amazing facility, and I'm very happy that I had a chance to work on and continue work with data from Hubble. But notice that basically 40 years has passed and we really didn't manage to increase that much the size. Granted, James Webb will push this and will increase the diameters, but we are speaking here about a factor of few over many decades. So why is that? Why this happens is what is commonly known as the space spiral. And let me just walk you through this. None of this should probably sound surprising. It is expensive to get to space. So missions are expensive. Because they are expensive, we build a low number of missions. So because we only build a few of them, we want to make them unique because we want to answer many questions. That means we have challenging science requirements. And then we end up with very few missions doing all very different specialized things with challenging requirements. And so there's not much tolerance for failure. And once you start speaking about 99.999% confidence level and higher, prices go up very quickly. And so this is a spiral. The problem, of course, is that there's an upper limit on possible costs. So the spiral cannot really continue. What it ends up is basically leading to fewer and fewer large missions. Okay, so that's a general problem, challenge. You may think that everybody in space struggles with the same problem, but this is not actually the case. This is, I'm not saying it's unique, but it's more typical to the space science missions. If you take a look at what the commercial aerospace is doing, is a different approach. They tend to build many identical units or near identical units of simpler things that in combination will provide a more cost-effective solution. So this is Skylink. This is one, perhaps the most illustrative example, where the plan is to launch over 10,000 identical small satellites to replace very large, very expensive communication satellites. Let me just point out this car. So you probably have seen cars like this. And you may think that this car costs about $30,000, but it depends when you buy it. If you actually bought the prototype of this car, this was almost $500 million. And that's true for most cars that are on the street. If you buy a prototype costs to develop a car prototype typically costs around $500 million. Okay. In astronomy, we end up building and buying prototypes and then building another prototype. So why? The question, of course, could we change the paradigm a little bit to actually benefit us better, given the changes that technology has enabled recently? And so we have started this discussion why we could not collect more light, build larger telescopes. And one of the things that you can minimize instrumentation increasingly effectively, and you can find more cost-effective launch solutions, and etc. But one thing that we found as a great limitation was the mirrors actually themselves and the optical telescope assembly. Not just the mirror itself, but everything that is required to support the mirror, ensure that it maintains its figure, it performs, it deploys as intended, and also to fabricate and create it. So I will just probably not go into details here. You can find this in our paper. This shows the history of telescopes, just focusing on the largest ones. What I want to point out, and I'm not sure if you can see my pointer. Can you see my mouse pointer?
Yep.
Yeah, great. Okay. Thank you. So that's basically, I missed Galileo just because it wouldn't fit Galileo's telescope even in the logarithmic scale here. What you see is basically typically gradual progress when you use a paradigm, and then you tend to reach a point where you just cannot even, it gets more and more expensive to, with the same paradigm, increase size. And then you basically progress slows down until you find a different way of building a telescope. And then you can further increase telescope sizes, but then you again get stuck once you reach the limits of your paradigm, and then you jump. And so we have seen at least 5 technological jumps in the history of telescopes. And that is how we managed to really create large leaps in sizes, not so much by the gradual refinement of the state of the art, but by bringing in novel technologies, okay? And one thing that is probably shared in all of these plateaus that people thought they figured out the best way to build telescopes. It's just telescopes, large telescopes are expensive to build. What I want to show you today, and this figure is too busy, I'm not going to go through everything, but we basically have facilities, very exciting facilities in the pipeline, Giant Magellan Telescope, 30-meter telescope, the ELT on the ground, and James Webb LUOR in space that will represent orders of typically an order of magnitude increase in collecting area. But to do the experiment I described, we would need something that is about 2 orders of magnitude greater light collecting area than, say, LUOR. So could it be possible to build something like that? And I think most would agree that if you would take the LUOR paradigm, which is basically building on the James Webb paradigm or any other existing paradigm right now, there is no way you could scale it up by 2 orders of magnitude. So is there a paradigm change that we could seek out that could enable us to collect more light? So, and this is just a quote that I think kind of drives home the point. The electric light did not come from the continuous improvement of candles. So there's a lot to be gained by refining existing designs, but we also have to look out for opportunities to change the game, and these exist, and they existed in the past. So one of the ideas that has been around for a while, we did not come up with this, even if it's not as well known in the astronomical community, is to replace primary mirrors with diffractive lenses. So you can use diffraction, of course, to change the direction of light. And you can use that not only to disperse light, but if you have a concentric pattern, you can use diffraction to concentrate light too. So we astronomers are not the only community interested in very large telescopes that provide high quality images. There have been 2 projects that, at least that I know of, that aimed at similar goals. What you see on the left-hand side is eyeglass. This actually is a prototype. It was developed by the Lawrence Livermore National Laboratory. This uses a single order diffractive pattern on thin glass sheets, in this case, a 5-meter diameter that deployed. It was from an origami-like configuration. This was a prototype actually to eventually build a 100-meter diameter telescope for observing Earth. This prototype was optically successful. In a very narrow wavelength range, it could deliver high quality images near diffraction limit, but it was too cumbersome to actually really implement. About 15 years later, the Moire project came to existence. This is a collaboration, or this was a collaboration between DARPA and Ball Aerospace. They used, instead of the thin glass sheets that don't survive very well launches, they used membranes, polymer membranes, in which lithographically they fabricated diffraction patterns. And the idea here is to build a 25-meter diameter space telescope that is launched in a compact configuration. The primary light collecting element is a diffractive, single order diffractive lens. This provide, in this project, the goal is to provide a low-cost telescope that can be launched temporarily in a geostationary orbit, for example, to monitor certain locations of interest. So these are published studies, and you can find really cool YouTube videos from DARPA and Ball on this project. These projects had some, while they were optically successful, they had some limitations that made it not well suited for astronomers. So one of them is that they had very long focal ratios, which makes it very difficult to really implement them. The other one was that they had strong chromatic aberration, which is less of a problem if you are looking at cars, for example, moving on the surface of the Earth, etc., because you can use a narrowband filter. But for us astronomers, we would want a telescope that performs well over a broad wavelength range. Progress has been made in the fabrication and design of diffractive optical elements. Some cool examples, if you are passionate astronomer with a deep pocket, you can now buy top-of-the-line lenses from Nikon and Canon. And these lenses are much lighter more efficient but very high quality imaging lenses than what was possible in the past. And the key difference is both of these companies developed diffractive optical elements, diffractive lenses, that are inserted into the traditional, conventional, fully refractive lens groups, providing more compact, lighter weight systems. So these provide very high quality images. They have also samples to prove that. That's one of the samples taken with this lens. Again, these are some of the best quality lenses you can get today. So over a couple of years, we have been working on trying to see how we could translate this kind of opportunities into large space telescopes. We published a paper in 2019, and there's also an SPI paper on this, a white paper to the decadal survey, and a range of invention disclosures and patents, some approved, some pending. I will show some of these. I will only be able to touch on a couple of the, what I think are the most interesting aspects now for this crowd. So as I mentioned that there were some limitations on both the eyeglass and the Moire designs in terms of the very long focal ratio and the strong chromatic aberration. So I was very fortunate to connect with Tom Milster in the Optical Sciences, College of Optical Sciences here at the University of Arizona. Tom is one of the world's experts in diffractive optics. And with him, we began an effort. He has led the design of an invention of a new optical element, diffractive optical element, which we call mode lens. These are multi-order diffractive element engineered material lenses. So that's a handful. So I will just stick with mode lenses. Let me just show you a cartoon how they work. And I will show you proof of that they actually do function. So the general idea here is that if you would take a conventional lens, right, you could shine light on it and it would give you a pretty good quality image. Now imagine that we want to make this lens lighter. So we can cut out plane parallel sections from this, and that will make it much more compacted. But it will introduce degeneracies in the light path, so you don't get quite the same quality image. Now, what we did in the last phase of the animation here is we removed the backside of the lens and we put another diffractive element there. So in a sense, you have now a triplet lens. You have two diffractive lenses, one a multi-order and another a single-order diffractive lens, combined with a refractive lens. And you can optimize all of these together. There's a very large number of parameters actually to optimize this. And you can get this from a triplet lens, and you can get an excellent quality. In fact, you can get better image quality from this lens than a regular apochromat lens, because the diffractive and refractive lenses have different direction in their chromatic aberration. So you can play those against each other and you can get a higher quality. Plus, it's a much thinner lens. We can create lenses, design lenses that are 2-3 millimeter thin, and they perform as a triplet. So this is from one of our patents. It shows the general concept. I will not go into the details of the optical design, but you can find some of those details in our paper. There's another paper coming up by Tom that provides even more details. The bottom line is that over intermediate bands with relatively simple designs, we can get very close to diffraction limited performance. And by the addition of a color corrector, we can actually extend that band very significantly. So this is not just simulations. Our team has built a mode lens prototype. You see in the left, this was one of our first prototypes, and on the center and on the right-hand side, you see that these are standard Air Force targets, and the UA softball field stadium seen from 186 meters, and in most cases, the lens brought about 21 arcsecond resolution, which was very good because this was one of the first lenses we fabricated with this new technology. It is also, in this case, this was made still of PMMA, so plastic lens, and didn't have any color correction. So and this was a very good performance. We have now, and I will show you examples of more advanced lenses, but this is a concept that is actually working. We have tested this under various conditions, and we have different testbed tests running. Okay, One great advantage of these lenses is not beyond being very thin and much lighter, is that they are easier to replicate and fabricate than the traditional mirrors. Okay, what you see here is an example for one of the labs that we are using to fabricate these lenses and replicate them. They can be molded. And that's a big advantage. So we create a metal mold, and from the metal mold, we can replicate lenses, and no further processing or polishing, coating is necessary for the lenses to function. So it's a much simpler process. Once you have a mold, we can create smaller lenses every 2 hours. And in fact, this is used worldwide for fabricating lenses, and not diffractive lenses, but regular lenses, this kind of replication via optical molding. We combine this with optical freeform fabrication. This is a newer technology. This is something that didn't really exist at least in a commercial level 20 years ago, but now this is something that you can purchase. And that uses an optical, basically an optical quality diamond tip with about 50 nanometer footprint to precision carve either some of the metal coated surfaces that we use for mold or PMMA and other materials. So these are some of the prototypes that we have created. This is an earlier prototype. This guy was still pretty sick, but you can see the multi-order diffractive pattern on the top. This is a different view, and if you see my pointer, you can see here something. It looked like the lens was scratched, but in fact what you see there is the single order diffractive pattern in the backside, and the combination of the backside single order, the front side multi-order diffractive pattern, and the refractive lens itself that gives you that optical performance. This is some of our newer lenses, much thinner, as we are learning about the fabrication technology. Okay, so the advantages of the mode lenses is that it can give you about 2 orders of magnitude lower weight than traditional mirrors, which is very important when you speak about space applications. But almost as important, maybe even more important, is that these mode lenses are, and that's typically true for transmissive optics, they are much less sensitive to misalignments and deformations than mirrors for multiple reasons. Both have to do with the geometry and the overall imaging system. I already mentioned the fabrication. They also have more flexibility in the optical design. Basically, by optimizing these 3 surfaces that really are part of 3 optical elements that are part of a single element, we could actually even add low dispersion spectrograph, for example. Okay, there are disadvantages. It's not a perfect substitute. It has a potentially narrower wavelength range with diffraction limited performance than a mirror. So this may sound like discouraging, but remember that James Webb is not diffraction limited either at shorter wavelengths. So you can do amazing science even if you are not right at the diffraction limit. Nevertheless, most of our design actually is designed to work at the diffraction limit, but that limits the bandwidth we can use. There's a trade. If you give up on the image performance a bit, you can extend your wavelength range quite a bit. So how do we go from small lenses to a 50-meter space telescope? So let me add here the asterisk. What we need for the transit observations that I described is not necessarily a single 50-meter space telescope. What we need is the light collecting area equivalent to a 50-meter telescope. Okay, we don't need to collect that light coherently. So it doesn't have to be an interferometer. In fact, basically, you just carry out these observations parallel, observing the same transit with, in this case, multiple telescopes, record the signal, and then co-add the intensity measurements. Okay, so the system that we need is quite simple, and this is just, we don't have a complete system design finalized yet. This is just a cartoon, but ultimately what we need is basically for our low resolution spectroscopy, transit spectroscopy, is a mode lens that collects the light. We envision currently 2 different arms, a near infrared and a visible light. These would be both equipped with a color corrector to further improve image quality, a filter with a prism, and a detector. The purpose would be basically single object spectrographs with very large collecting area. So we asked the question, what is the simplest way to build a telescope that collects lots of light and to build many of them? So what you see here is our current idea. This is not a final design, so there's no many details that are not worked out. What we did was we asked the question, what are the big possible stumbling blocks, and are there possible solutions for that? And right now, as of now, we found one or more solutions for every potential challenge for this design, but it's not a final design, okay? So this is how a deployed Nautilus unit telescope could look like. On the top, you see an 8.5 meter diameter mode lens. So this is really the only truly novel component. Everything else here is basically building on existing heritage. There's an instrument package in the center. The blue band is a solar panel, and it looks like a balloon because it is a balloon in a sense, not the lens itself. The lens is a rigid lens, but the white part that you see here, the outer shell, is inflated with a gas canister. It is not an essential part of the design, but we looked for the simplest way to actually deploy something. And inflation turned out to be a good idea. It may sound revolutionary, but again, we cannot claim credit for this. In fact, one of NASA's first satellites, the ECHO satellite, was an inflatable large balloon, and a separate project with some overlapping team members at the University of Arizona is developing inflatable space antennas led by Chris Walker that also use this inflatable, somewhat similar inflatable technology. Okay, so why would we do this? Why would we want to inflate it, the telescope? So this is again a cross-sectional view, and the idea is that we want to launch this in a compact configuration. So we want the 8.5 meter lens to basically fold into a launch container. And we want to do that because we don't want to launch just one, we want to launch many units. And this is possible because actually the rockets that and the fairings that will be available that can launch large diameter optics will also have a very large useful volume. So we can, depending on whether one would go with the Nautilus, the SpaceX now called Starship fairing, or the NASA SLS-B2, you could put in somewhere between 15 to maybe 23 unit telescopes into a single fairing. Let me show you how these are just examples. Of course, SpaceX is kind enough to build us the rocket we need. And let me just show you a cartoon, a sketch of how this would work. So our rocket, once it's in orbit, would release one by one the telescopes, the individual units. The individual units are all identical. They would be inflated, not the lens. The lens is rigid, but the external shell would be inflated by simple gas pressure. And okay, these telescopes are again not a formation flying interferometer. Their relative position is irrelevant. What matters is that they can look at the same target, observe the same transit, and then digitally code the signal. So these containers disappear somewhere. It's we would obviously launch them far enough that this would not be a concern. And then we could use this array to observe. You could use them as individual telescopes, and when there's a transit event that you want to observe, you would turn all the telescopes to the same target. So this is just another view of the deployed unit telescope, a launch container, and how launch containers are stacked together. So what I want to emphasize here is that these are large. On the right-hand side, you see the approximate size. 8.5 meters is the nominal size. And that is larger than James Webb, Hubble, and Ariel combined in terms of light collecting area. And the promise here is not just to build one, but to build it in a way that it can be replicated cost effectively, and we can share also launch costs. So the idea is not just to build one, but to eventually build up 35 or so. That would give you light collecting area equivalent of 50 meter space telescope. That is what we need to survey 1,000 exo-earths for biosignatures, for example. So we call the concept the entire observatory, when you have, say, 35 of these units, the Nautilus Space Observatory. And I described that concept. We have put into the Astro 2020 Decadal Survey, we put in a suggestion for a Probe-class mission. And the Probe-class mission would be building the first such unit. We think that it would fit within the Probe-class budget. And then once that unit is working, we have a good basis to replicate it and then create an array of identical units. Let me show you, there's a lot of work going on and I will not be able to touch on everything, but I just wanted to show you a couple of pieces of hardware to see what we are working on. So we have a very generous funding from the Gordon and Betty Moore Foundation that made it possible for us to realize many of these ideas and simulations. So we are advancing currently the optical design, we are advancing the optical fabrication techniques, we are increasing the lens sizes and demonstrating efficient replication. We are pushing the optical quality assessment, surface metrology, and then we are also building a telescope that we will use by the end of this year to demonstrate the mode lens technology as an actual astronomical telescope on sky. So one of the questions, important questions, how do we go from small diameters to large diameters? And we have multiple paths identified. I just mentioned here two most interesting ones. So we can create segments, segmented molds, so mold segments that we can assemble into a large mold. And then from that large mold, create a monolithic lens. So that would be one possibility. The other possibility would be that we create smaller mold segments. So this would be 1.5 meter diameter roughly. And then we would use those segments to mold lens segments and then assemble the lens segments. We are currently pursuing technology development on both paths to see which one will be the best to go forward with. I should point out that even though this is not so widely recognized as a technique or understood as a technique, in fact, this kind of diamond turning based mold segments, etc., this is not something that is truly novel. During the Strategic Defense Initiative, large diamond turning machines were developed. And Lawrence Livermore, for example, they had this large optics diamond turning machine. And the Keck telescope's secondary mirror, in fact, was diamond turned in that facility. It was able to do 1.5 meter roughly diameter, excellent quality optics. With that size of that diameters, we could already create the lens segments and build a large lens, but we can maybe push this further too. So an important consideration there, how do we align and fuse mold segments or lens segments if we want to mold a monolithic or a segmented lens. I want to show you that there is commercial applications into the diamond turning. So we are happy to work with the Korean Basic Science Institute, who have an excellent group on diamond turning, and on smaller scales, we are working with them and exploring how to scale up this technology. This is a picture that was taken about 10 days ago in the UA workshop. We are building a mode lens-based telescope. This is first pieces that are coming together. This will be a 0.24 meter diameter lens-based telescope that we will attach to one of our large telescopes here in Arizona. This is one of the prototypes of the diameter for demonstrating the lens diameter that we will use. We are also pushing forward technologies to align these lens segments or mold segments. I will not go into this, but we have, our group has patents pending and invention disclosures on this. And you may see here in the upper right a movie that shows a white light interferometer that is actually measuring the tilts of these lens segments and can align them. It's important to recognize here again that our alignment problem is typically 100 to 1,000 times less difficult than if you are trying to align segments of a mirror. And we are not envisioning an active alignment system. This is just part of the fabrication process if we go down that path. So I mentioned we already put in a Nautilus Probe class mission to build a single 8.5 meter diameter telescope that would revolutionize exoplanet science, but also time domain astrophysics and studies of faint objects. It's more collecting area than James Webb, Ariel, and Hubble together combined. So if you are interested in reading more about that, the Nautilus Probe, I refer you to the white paper, or feel free to email me. I don't have too much more time, so I will not spend much more time on it. But I want to point out that this basically would be much more capable than anything currently envisioned for transmission spectroscopy. Cost estimates, it's an important question. How much does it cost? We don't have a complete design. So at this point, these are exploratory cost estimates, but we have done two. And there's a graduate student working full-time on the cost modeling. We get two slightly different estimates. If you scale down from James Webb, I will not go through the details unless someone wants to hear more about it. You end up with about a $2 billion estimate. If you actually break it down from the bottom up and define the tasks that we think you would need to do, this is what we did. We created 42 tasks, created cost and time models for them, and then ran many Monte Carlo realizations. What we end up with is basically this, you see a cumulative cost profiles, and we end up with a budget that is below $1 billion. Again, at this point, these are exploratory estimates, but they show that there is a potential to build these diameter telescopes for a much lower cost. So I'm coming to the end here. In summary, we have developed and further advancing a new technology called multi-order diffractive engineered material lenses, or MODE lenses. In addition to the astronomical applications, we think that they are also commercially important. This is something that can also revolutionize, for example, commercial drones, etc., where weight and alignment tolerance are important. And then we have developed an observatory concept. It's an exploratory concept, but we went through all the key things that could be potential showstoppers. And I think we could find multiple possible viable solutions for them. So this basically translates in ultra-lightweight optics that can be cost efficiently replicated. So we are envisioning launching an array of lightweight, low-cost, identical telescopes that can be launched simultaneously. So that way, the risks and functionality are shared between the units. The per unit cost goes down significantly. And as such, it would represent the paradigm change for space telescopes. We would have scalable, highly sensitive, low-cost telescopes. You could imagine just say you need more telescopes, you could just replicate them, add more to the fleet. We propose Nautilus Probe as a single unit to demonstrate the concept and also transform exoplanet science. And then if that's successful and we demonstrate it, the next step could be just to replicate it and then build up a space observatory with 35 or so units launched simultaneously in 1 or 2 rocket launches. And that would enable us to characterize about 1,000 potentially Earth-like planets in the kind of detail that we would need to look for biosignatures. Thank you.
All right, thank you, Daniel. If you would like to ask a question, please use the raise hand feature under the participants tab. We have a couple of questions in the chat as well. So first off, how thick would the 8.5 meter lenses have to be to support its own weight and the launch vibration loads? Are there radiation hard glasses that can be used for molding?
Yes. So okay, let me show you okay. So the launch survivability is, of course, an interesting question. And so we have looked into it. We have not solved it. Can you see the slide that I'm showing now?
Yes.
Okay. So basically the launch survivability is a combination. It depends on the acceleration curve from the rocket. And then we have to consider what is the inherent strength of the material, the structural strength of the overall design. So one possibility is that we may be able to design a self-supporting structure that is able to survive the launch itself. And so it's maybe worth pointing out that these kind of structures are not quite unheard of in space. For example, if you consider the ISS has very large solar panels that are a combination of glass and metal structures, and it's not a problem to launch them. Of course, this is not an identical case, but it's not certainly something that is unheard of. We also identified another way in which the launch container itself would include support structures that are optically not important, and they would be basically going away with the launch container for most part, but they would be able to dampen the vibrational modes that are introduced during the launch, and that could be a good way. There's also a third pathway. This Northrop Grumman holds a patent to launch sensitive optics and large-scale optics. In this case, it's a very interesting idea. The launch container would be filled with carbon dioxide and then frozen. So it's basically the lens is frozen into a carbon dioxide ice. And once in orbit, the CO2 sublimates cleanly, leaving the lens there. So that's one of the, we don't have a final solution yet because the design is not final, but we see multiple possible pathways forward. The other question was, sorry, there was launch survivability and there was, glasses. So there are a range of glasses that are well suited for molding, and they can be radiation hardened. It's not a problem.
All right, question from Laird.
Oh, yeah. Hey, Daniel, thanks for the talk. It's really nice to see how much progress you guys have made on this project. It's quite impressive. One question I had, and I guess, you know, everyone's sort of, I mean, the tricky thing about this is having a large curved optic. Now, obviously, the curvature of that optic must be setting your focal plane position, I'm assuming, right?
So actually, we can, so not necessarily, because most of the focusing effect will come from the diffractive component. So actually we can make, currently most of the lenses we are making are flat lenses, and because of the diffraction.
Okay,
pattern.
you know, I get that.
So the curve, okay.
Okay, well, maybe I misunderstood. Sorry. So the curve, you're not using the curvature of, my impression was that it's a large curved Fresnel lens.
So my colleagues really don't like if I call these Fresnel lenses. So they are much more advanced. The curvature is not the primary component for focusing. We can actually, so that actually adds, it makes it easier. So we can combine the refractive and the diffractive components, and it does help. And it's also mechanical. We actually keep it mostly in the design spherical for now, because it also provides actually a better mechanical stability against vibrations than if you have a flat membrane-like structure.
Okay.
But it's not really.
That was just my, that's the only thing I wanted to touch on, is that the radius of curvature, you know, normally that's going to be where you're going to have your slit, I guess, for your spectrograph. And is there an issue with thermal CTE effects where the curvature might be somewhat variable depending on the angle of the sun hitting the instrument, that sort of thing?
So that is, so we have looked into CTE effects for some aspects, but we didn't do a complete analysis. I should point out that, so that's one of the, so illumination by the sun is a very important component, and we did not design yet sunshades to this, just, you know, baffles, etc. In this current configuration, probably would not work because you would have enough scattered light, etc. So somehow this needs to be shrouded with a cylinder-like structure potentially, or we have multiple ways. It's not a solar shade sun shield is not very difficult to add, but that would definitely be a problem also because you would add basically scattered light background that could be systematic. So we would want to shield it from the sun in a way that it's minimizes those issues.
These lenses are lovely, but they do scatter light quite a bit. You don't want to have a bright source like the sun.
That's right. Yeah, the sun, not definitely. And I think for the CTS, maybe it's also worth adding that again. And so we did studies on that. These systems are 100 to 1,000 times less sensitive to misalignments than actually a mirror. So I guess that's one of the reasons why we are not using mirror-based glasses ourselves, because it would be a real pain to have little reflectors. So that helps also with this kind of effect. The other thing is that actually for transits, we really don't care about ultimately the image quality. We are trying to design these to be diffraction limited so that we can do a broad variety of science. But, you know, Kepler is very far from diffraction limited imaging performance on the detector, and TESS is again.
Yeah, I mean, it really helps you make a smaller spectrograph. If you could have a bigger spectrograph and still collect the same amount of light.
That's right. Yeah. So we are looking, we don't have a design that's complete enough to really do CT analysis, but you are right that that's something that will need to be looked at. Great.
All right, we should move on to the other questions. The next one that came up was in the chat from James Casting, asking if Nautilus would be deployed at L2.
So that would be a potential orbit that we have thought about because of the thermal stability, so that could work well. We have also now played with, but we didn't do trade studies, with something like a test-like orbit, which is would also provide long windows of visibility and well-controlled environment in terms of the scattered light. But we haven't completed a trade study. The L2 looks like a pretty safe bet. It would work there very well.
All right, next question is from Tad.
Hi, Daniel. Great talk, as always. So my question is pretty similar to, I think, Ravi's in the chat. Basically, people have shown that both for transmission spectra and reflected light spectra, clouds can really impact the detectability of biosignatures. And so the advantage of Nautilus seems to be that you can really enhance the integration time because you have such a wide array of telescopes. You can spend some time staring at an individual system. So what sort of PPM do you expect to achieve? Do you think that you could get past this cloud issue with Nautilus?
So the cloud, yeah, thanks for bringing that up. So the clouds are, I get this question often, and I have actually a slide for this. So the clouds are, people often think that clouds can be a general problem that prohibits us from actually studying these planets, but it is really a signal to noise question, and you alluded to this too. So for example, there is a simulation on the left-hand side with how HST sees, this is from Laura's nice work on GJ1214P, and there is basically a model below. That model was not fit to the data. It's a representation that's a model that's consistent with it. And the point is not so much that clouds erase features completely, but clouds dampen the features, especially that those are below the cloud deck. So if you have high enough signal to noise, you can counter that. So the simulations I showed, they were typical in a 1 part per million or a few % of that. That's basically a little bit worse than the photon noise we expect to get from Nautilus. And in fact, right now, most of the space telescopes that we have that have done this kind of studies, they were actually very close to photon noise, even if they were not designed for that, for example, with HST. So the clouds, there are basically two solutions for those. One is actually simply taking good enough spectra that they don't kill your features. And the other is that to have a large enough sample that even if a small fraction of them somehow would be reaching ultra high hazes, you would still have a large enough sample to study. So, and as you pointed out, this is not actually, while with the same size telescope, this is more of a problem for transmission spectroscopy than for high contrast imaging, but it also impacts high contrast imaging. And in high contrast imaging, you are really speaking about increasing the contrast by something like maybe 5 orders of magnitude with respect to state of the art. Here we are keeping state of the art sensitivity and stability, but increasing the diameter. So hopefully that addresses the question.
All right, that is our time today. So let's all unmute and thank Daniel for a very
well, Kimber, sorry, yeah. There are more questions. So if you, we could answer the question after this.
The ones in the chat?
Yeah.
Right, so there's one about where are we going to find these terrestrial planets? And it seems like there was a discussion that resolved that. And then Ravi's question was also asked by Tad. So I don't know, Daniel, do you want to comment briefly on where we're going to find the planets, since apparently this was not resolved?
Yeah, so that's a good question. So there are two options for these. Right now, we don't have 1,000 transiting habitable zone planets that would be suitable. So you could either do it as in a precursor mission, or you could do it as part of the mission here. And so we have actually both designs available. You could launch one or more of these units, for example, on a smaller scale, say a 1 or 2 meter, and create large field of view, but narrower wavelength range survey telescopes. And you could search for those that way. One configuration I did not show here is to have in addition to the main lens on front that is well suited for spectroscopy, have a smaller but wide field of view lens in the back. And so you could use, when you are not observing transit spectroscopy, not doing transit spectroscopy, you could use the wide field of view lens on the back with all these units to monitor the sky and look for transits. And if your system is good enough, maybe during the transit, you could actually turn it. When you are discovering them, you could even turn your telescopes, but you could also just return later to that.
All right, any final quick questions? If not, let's all thank Daniel for a very interesting talk.
Thank you.
Great talk.